All right, here we are, stoichiometry. I want to go ahead and get started with our unit, and we're going to go through a couple of examples as we continue. So you want to make sure that you stay focused, stay in here with me, and we're going to see what we can do. Now, the idea that we're using behind stoichiometry is usually when we look at a recipe of any type, it usually tells us what we need, but not only what we need, but how much we're going to need. This is going to be the same process that we need for stoichiometry. If we need more, then we can adjust accordingly. But we're starting off with the exact measurement of what we're going to need. Now, this recipe, quote unquote, that we're using here is going to be our balanced equation. Now, this part coming up here, this is for more for your filling in your notes. So if you have your guided notes, you can go ahead and follow along. If you need to pause, go ahead and do so. But stoichiometry is Greek for measuring elements. Now, defined as the calculations of quantities in chemical reactions based on a chemical equation or a balanced equation. There are going to be four main ways that we're going to look at this, paying very close attention to number 2 and 3. The first way is in terms of particles, second in terms of moles, third in terms of mass, and fourth in terms of volume. Now, in terms of particles, we're saying that I could read this equation like a sentence. It's saying that 2 molecules of hydrogen react with one molecule of oxygen to form 2 molecules of water. Now, while this is very good and very helpful, it doesn't help me at all in terms of being able to do any calculations or real reactions because I can't manipulate individual molecules. But when I move into my next stage, which is in terms of moles, I sort of have a way that I can start to move. Now, the coefficients from our balanced equation are going to tell us how many moles of each substance. Once we understand how many moles of each substance are there, we can then branch out and look into the other directions. Now, that means if I'm reading this equation, it will be 2 moles of aluminum oxide yield 4 moles of aluminum and 3 moles of oxygen gas. Now, remember that this is just a mole ratio. It's just telling us how many of each will relate to the other. Now, speaking of mole ratio, this is going to be what we're going to use a lot. A mole ratio is going to be the moles of our new substance divided by the moles of our old substance. And this is always going to be right there in the middle of your calculation. If we're doing stoichiometric calculations, you have to have your mole ratio involved. Now, just to give a simpler version of how we usually would talk about it, or what you'll hear me say a lot is your mole ratio, and I'm just going to abbreviate MR, equals moles you want divided by moles you have. This is so it keeps in line with our usual canceling out of units, and we can make the transition well from one unit or from one compound to the next. So you want to make sure that you are paying attention for this. Now, the other key point is that the numbers are going to come from the balanced equation. I don't know how many times I can say it, how many different ways, but the numbers that we use for our mole ratio come from our balanced equation. So if you need to go back and look at your balancing equations again, take some time. There are a couple good videos online that you could use. Now, moving on. The next way that we could look at it is in terms of mass, and this is where we look at our law of conservation of mass. Now, remember, that means that matter cannot be created or destroyed. It's just rearranged in a chemical reaction. So we can use this information, using the moles that we have, we can check the mass on both sides. If it is equal, then that means we're on track. If it's not, then that means we have a problem. So, using the example of 2 molecules of hydrogen plus 1 mole, of oxygen are going to produce 2 moles of water, I got to do a couple of quick mole conversions. So, 2 moles of hydrogen gas, and I just set up my table like normal. 2.02 grams of hydrogen are on top, so I'm just going to multiply what's on top and come out with 4.04 grams. have to do the same thing for my oxygen. I only have 1 mole of oxygen, and each mole of oxygen has a mass of 32 grams. So when I add that all up, I have 36.04 grams for my reactants. Now, to make sure this is in line, I have to make sure that on the other side I have the same thing. So, for my products, I have 2 moles of water, and each mole of water has a mass of 18.02 grams. Multiply across the top, divide by what's on the bottom, I get 36.04. Right now, it looks like everything matches up. I'm going according to my law of conservation of mass. Now, the mass of the reactants must equal the mass of the products. This is going to be a key. Now, last but not least, in terms of volume. Now, in terms of mass and volume, once we know and can interpret our reaction in terms of moles, it becomes very easy to do the rest, because we know that 1 mole of any gas at STP is going to be 22.4 liters. Using this information, we can convert between gases and still be able to get our final answer the way that we need it. Now, note red flag, red flashing light. You want to pay attention to the fact that the only 2 things that are always conserved, are going to be your mass and atoms. Always. Mass and atoms are always conserved. You notice the other ones will change, and that's going to be a key point. You want to pay attention to the fact that the other ones will change, but the mass and the atoms will remain the same. Now, we want to go ahead and take a moment. We're actually going to skip through the next slide fairly quickly. We want to take some time and look at how we would set up our conversion factors accordingly. Now, if I have this balanced equation given to me, it tells me that every time I use 2 moles of aluminum oxide, I'll get 3 moles of oxygen. Depending on which one I need, I can set up my conversion factor accordingly. If I'm given oxygen, I can set it up where oxygen will be on the bottom so I can cancel out my units, as well as if I'm given aluminum oxide, the vice versa would apply. These are things that you want to keep in mind, because for any reaction, there can be multiple different ways that you can organize your mole ratio. Now, let's go ahead and start with a mole-mole conversion. So, according to our information, how many moles of O2 are produced when 3.34 moles of aluminum oxide decompose? So, since we're going mole to mole, we want to pay attention to the fact that we're going to start with moles and we're going to end with moles. Our given here is actually going to be 3.34 moles of aluminum oxide. This is where that's going to be very key. And I need to convert that now to moles of O2. Sorry if I crossed it out a little bit. Now, let's go ahead and I'm going to go to another page and we're going to go ahead and get started with this. Now, since I have my, there we go back to my black marker, 3.34 moles of, aluminum Al2SO4. Ooh, sorry, I messed that up. Al2O3. There we go. Now, since it asked me how many moles of O2 will be produced, I need to make sure that my moles of Al2O3 go to the bottom so I can cancel it out. And according to my balanced equation, I have 2 moles. Now, on the top, since I'm going to moles of oxygen, then I need to look at my balanced equation to see that I get 2 out. So, now last step, since I needed to end in moles of O2, all I'm going to do is multiply by my 3 and divide by 2. So 3.34 times 3 divided by 2 gives me 5.01 as my answer. 1 moles, and now you should notice that I'm in O2. This is my final answer for this step. We're going to go ahead and come back at another time so we can finish up. and do another example with mole to gram conversions. Have a great